excuse me, many equations can only be solved graphically because we don't have the function. So, by methods of successive. So the way we can do that is by successive approximation to roots, called iterative methods. There are three methods in your bird book. The middle one of the three, somewhat cumbersome, and I looked at that and thought not really necessary. So we're going to have a look at two methods. The bisection method we're going to have a look at today, and then next week we'll have a look at Newton-Raphson's formula method. So each of those you're going to need for one part of the assignment that I'm giving you. I'm going to be issuing that today, so you can start working on that as we go through the coming weeks. The bit where you're going to look at a function, the bisection method, just I'll start on that if you so wish. Just as a precursor, what I want you to do, without calculator, without the square root function on the calculator, think about how you would do that while I go and get my make an initial estimate. For each of the iterative methods, we require an initial estimate made to the root that we're interested in. So if we look at the one method would be to graph the function either by hand, sketch it with a few points to see what it looks like, to get a rough estimate of where the roots of interest are. The other way is to use functional notation and look for a change of sign, because the results of the function are going to change sign either side of a root. So if we look at this function here, y equals x squared minus x minus 5, we can estimate from the graph here that we've got a root between x is equal to 2 and 4. Okay, in fact between 2 and 3, you can see from the graph. Okay, and also we look at f of x minus 2, you get a result of minus 3, and when x is 3, we get a result that's positive. So that change of sign between negative value of y, positive value of y, means there must be a root somewhere, at least one root between those two values of x. Okay, so that's two different methods of obtaining an initial guess of where the root of interest is. Because there's two, we might be interested in the negative root here, we might be interested in the positive one, we might even be interested in both. Bisection method. So, use the method of bisection to find the positive root of the equation of 5x squared. So the first step, use functional notation or graphical methods of the value of x that are inside the point. So we're looking here at this graph. We've got a root somewhere around about where x is equal to 1. The graph is not detailed enough to be able to see exactly whether that root is exactly 1 or not. So we're going to have a look at it using the iterative. First of all, though, use the quadratic formula, find the root that function. So we kind of know where we're headed. So using the quadratic formula, what are the two values, the two roots for that equation? 1.047. What are we looking for in terms of three significant figures? So that would do equals 1.03. Three significant figures, doesn't it? And the other one, just for completeness, -1. But this is the one of interest, the positive root. Okay. So we've had a look at it with the quadratic formula. Okay. There's a way of knowing whether we're on the right track to do this with the iterative method. So the graph says, or suggests, positive root around equal to 1. Yep. At the top here, using functional notation, when x is equal to 1, the function equates to an answer of -1. Guess that we're underneath the x-axis. When x is 2, the function equates to +25. So we know we've got a root somewhere, using functional notation, between the values of x equals 1 and x is equal to 2. Okay? So, I mean, it's pretty obvious. We already know it's very close to 1 here, right? But you might not do that in all cases. Okay? So, second step of the bisection method is to find the midpoint between the two limiting values for x. We're calling them here x1 and x2. So you simply add those two values together, 1 and 2 in this case, that's what we're using from up here, to end up with a closer guess or a closer approximation to the root. We then use the functional notation to find out whether we've changed sign. Okay? So we look at the function when f is 1.5, the value of our new guess comes to 10.75. So the value 1.5 is still above the root we're looking for. Since the value at 1 is negative and the value at 1.5 and 2 are both positive, the root must lie between x is equal to 1 and x is equal to 1.5. So the next step, find the next guess. In my method I've called that x4. I'm looking between the x1 guess when x is 1, 1.5, coming up with a new guess to our root of 1.25, plugging that into the formula there, to find that it's still positive. So there must be a root between 1 and 1.25. So what we need to do is carry that on until we get the two values two successive values that are the same three significant figures. So have a go at that, see how you get on. What have you got for function at 1.25? Hang on. So the next difference, the next difference is the result of that is, what have you got? That's 1.703, which gives, so our root to three significant figures here is 1.13. Yep, that's that value in there, three significant figures. So we're still above the x-axis at that stage. So what's halfway between 1.25 and 1? .0625. The result of that was should be 1.0625. So our root to three significant figures there is 1.06. Halfway between 1.0625 and 1 is 1.03125. Result of that function is minus 0.338. Yeah. So our root there, the three significant figures, is 1.03. At that point, we've changed sign now. So we've now got to look between 1.03125 and 1.0625 now. Got to stop looking between 1 and the top figure. Got to look between these two. So halfway between those two is 1.0468. The answer to that is 0.0624. Our root now to three significant figures is 1.005. Okay. We're still negative, so now we've got to go between those two figures. Yep, we've got to bisect those two. So we're looking for a function at what's halfway between those two. Halfway between those two. That one, and, sorry, that one and that, then that one. Then two. That one was negative as well. We've got to go between these two. Halfway between 1.0625 and 1.0468. that root, we can already see that root, the three significant figures, is 1.05. Therefore, because those two values, three significant figures are the same, we can stop because we've got the answer to the number of significant figures or decimal places that we're looking for. Okay. All right. So there is repetitive. That's what iterative methods mean. Okay. The method we'll look at next week, Newton-Raphson's, is quicker, but you can only use it if you can differentiate the function. So that's the issue with that. All right. So you must with a function that you can't, you need to use this method. So let's have a look at another example. This time, use the bisection method to determine the positive root of the equation x plus 3 is equal to e to the x, corrected 3 decimal places. In this case, finding the root is going to determine the value of x when the two sides of the equation are equal, i.e. here I've graphed e to the x, that blue line there, and we graph x plus 3 there, and they meet up here. There's probably another place where they meet somewhere over here somewhere that's not on the graph. We're interested in the positive root. We're going to find the value of x when these two values meet, and when we could plug that into the function and find the x and the y points where they meet. Okay. First thing we need to do here is rearrange that equation so it equates to 0. So here's our function x plus 3 is equal to e to the x. So simply take e to the x from both sides. Then that's the function that we're going to actually use iterative methods, or you're going to use iterative methods now, solve. Yeah, that's in. We've been grafting that for. So I've graphed one side, x plus 3, and I've graphed the other side, e to the x. Equals, that does, yeah. You can't see it very well. I'll write it up there. F of x equals e to the x. That green one, f x equals x. Right. Okay. To see what you're saying now, it does look like a negative sign. Also, the graph here suggests there is a positive root between x is equal to 1 and x is equal to 2. Further proof of that is using the functional notation. X is 0, the function equates to plus 2. F is equal to 1, it equates to 1.2817. When it equals 2, it changes to negative. Therefore, we've got a root somewhere between 1 and 2. And we're going to try and find that using the iterative methods, 3 decimal places. So, just start and using the table to actually find and add the values in each time. That's a little bit tidier way to record the values. And we're recording here x3, the new guess for the root each time. The 3 decimal places over here looking for that to be the same twice, then we can stop. So I've done the first ones. I've included the FO, the F1 and F2 at the top here, values of them. 1 and 2 halfway between end up with a root of 1.5. When we're function as 1.75, we end up with 1.75 and so on. So the idea here is to carry on with that table till this number in the end here, 3 decimal places, doesn't change. 2 iterations. Yep, equate the equation to 0, yeah? So we're going to say that fx is 2 ln x plus x minus 2 equals to 0. Yep. What are we going to start with using the functional notation? Find a first guess. Where did I start in the last problem? Yeah, I'm not going to do a graph this time. X is equal to the f at 1 is 2 times the natural log of 1 plus 1 minus 2 equals